Konnichiwa. Today is the third and last of our lectures on double integrals. In this one, we will be talking about double integrals in polar coordinates. Most of you will have already met polar coordinates before in a previous math class or maybe a physics class, so I will do just a quick review, or maybe it's a quick crash course if you haven't met them before. Either way, we only need a few basic facts about polar coordinates in this class. The main thing is that polar coordinates give us an alternative way to provide points in the plane with addresses. In the ordinary rectangular coordinate system, which we all know and love, we know how to assign addresses to points. Given any point in the plane, we just ask ourselves, how do we get to that point from the origin, moving parallel to the axes? In this case, we start at the origin, we move horizontally a certain distance to the left, and then vertically a certain distance. And if it happens to be that we move, say, 3 units to the left and 11 units up, then we would say that the coordinates of this point are -3, 11. The negative because of the leftwards direction when we moved horizontally. Every point in the plane has its coordinates, and given any pair of coordinates, there's some point in the plane corresponding to it. All this is so familiar that it's easy to forget that this isn't the only way to assign coordinates to points. The second most common way to assign coordinates to points in the plane is via the so-called polar coordinate system. In the polar coordinate system, we still of course have an origin, and we have one special ray that we call the polar axis. Now, given any point in the plane, I have to tell you how to assign polar coordinates to that point. These will be a pair of numbers, of course, the first of which is very straightforward. It's just the distance of the point from the origin. So if this distance is r, then the first polar coordinate of our point will be r. As for the second coordinate, that's just going to be this angle, the angle we have to rotate the polar axis through in the usual counterclockwise direction to get to this line joining the origin and the point P. So our second coordinate is theta. For example, if I mark off 1 unit on the polar axis to give a sense of scale, then I could say that this point, which appears to be 1 unit straight up from the origin, would have polar coordinates 1 pi over 2, because it's 1 unit from the origin, and I have to rotate through a right angle to get there. Similarly, this point seems to have the coordinates √2 pi over 4. √2 because it's the diagonal of this unit square, pi over 4 because to get there I have to rotate through that angle. This point down here looks like it is at 3 pi over 2, because it's 2 units away from the origin, and we have to rotate through 3 pi over 2 to get there. Well, you get the idea, but you may have noticed an ambiguity about the second coordinate. For example, in this last point we looked at, sure, we could describe it as 3 pi over 2, but couldn't we also describe it as 2 minus pi over 2? We should be able to reach that point by rotating pi over 2 in the clockwise direction. Is that considered legitimate? It is considered legitimate, and it's more complicated than that. We don't just have to think about going around counterclockwise versus clockwise. We could also add on any integral multiple of 2 pi and get a different angle that way. I could reach that point by rotating through a full rotation and then 3 pi over 2. In other words, I could let that angle be 7 pi over 2. Fortunately, we don't really have to worry about these complications in what we'll be doing in this class. In a class in which you go into polar coordinates a little more thoroughly, you can explore the consequences of such ambiguities. And those things really come to the fore if you ever learn how to do calculus with complex numbers. But that's just something to look forward to in the future. For the most part, we can just restrict our attention to cases where the second coordinate theta is between 0 and 2 pi. Well, with 2 different coordinate systems to play with, one of the first questions that arises is how do we translate between the two of them? For example, if you give me some points rectangular coordinates, or Cartesian coordinates as they're sometimes called, how can I translate them into polar coordinates, and vice versa? If I give you a pair of polar coordinates, and you only speak Cartesian, how are you going to translate those over into rectangular coordinates? Well, this turns out to be very easy once you establish a convention about how to relate the Cartesian axes and the polar axis. And the convention is simply to superimpose the 2 origins and let the polar axis lie along the positive x-axis. Like this. So now our problem is we have a point in the plane. We can give it 2 different sets of coordinates. Its polar coordinates, r and theta, or its rectangular coordinates, which we get by moving a certain distance along the x-axis and then moving a certain distance parallel to the y-axis, those two distances being the x and y coordinates of the point. So our task is to figure out how to translate from r and theta, the polar coordinates, to x and y, the Cartesian coordinates, and vice versa. The most basic right-angle trigonometry does the job for you at a glance. Pray to 𝐶𝑎𝑙𝑙𝑢𝑠 and he will tell you that x is r cosine theta, and that y is r sine theta. Well, that was easy. But suppose we want to go the other way around. Suppose we're given the Cartesian coordinates and want to translate into the polar coordinates. Well, first let's think about r. I want to get r in terms of x and y. Well, now I just have to pray to Pythagoras, and he tells me what to do. R squared is going to be x squared plus y squared by the Pythagorean theorem. Yes, I could take square roots of both sides to write that in terms of r instead of r squared, but I'm not going to for two reasons. One, square roots are ugly. And two, there are situations in which we want to allow for negative values of r in polar coordinates. We're not going to need them in this class, but I want to leave that possibility open. If I take square roots of both sides, then strictly speaking, I get r is plus or minus the square root of x squared plus y squared, which is very ugly indeed. So let's leave it in this pretty form. Okay, and we still have to get theta in terms of x and y. Once again, 𝐶𝑎𝑙𝑙𝑢𝑠 answers all your prayers. 𝐶𝑎𝑙𝑢𝑠, aha, tangent. So the tangent of theta is y over x. And once again, I'm going to refrain from taking inverse tangents of both sides, and for a more pressing reason here. If I were to write theta is inverse tangent of y over x, well, remember from your trigonometry days, and this is a little more sophisticated than 𝐶𝑎𝑙𝑢𝑠, that the inverse tangent is restricted to the range from minus pi over 2 to pi over 2. Well, I definitely do not want to restrict myself to that range, because I want theta to have values in the second and third quadrant as well. So we'll just leave it like that, keeping all of its ambiguity intact, without eliminating any possible values of theta unnecessarily. Good. Well, these translation equations between the two systems will be your friends whenever you are working with polar coordinates. I'll mention for those of you who maybe have never seen polar coordinates before, that the advantage of the polar coordinate system is when we are working in situations involving orbits or where there's some sort of a point of rotational symmetry. As a quick example, just consider the unit circle. As everybody knows, the Cartesian equation for the unit circle is x squared plus y squared is 1, which may seem pretty simple, but on the other hand, it's pretty complicated when you compare it to the circle's polar equation. What's that going to be? Well, the circle consists of all the points that are exactly 1 unit away from the origin. In other words, all the points whose first polar coordinate is 1. No matter where we are on this circle, the first polar coordinate will be 1. That means that the polar equation for this curve would just simply be r equals 1. Which is surely as simple as you could hope for. On the other hand, lines in the plane have very simple Cartesian coordinates. Expressed as polar coordinates, those things are appalling, so we're not going to do that. The whole point is you use whichever coordinate system best suits the situation at hand. I'll give one more example to make this clear, and to give us a little practice with these translation equations. Consider the Cartesian equation x squared plus y squared is 2y. Well, this is a second-degree polynomial in x and y, so it's definitely some kind of conic section. You might even see that it's going to be a circle. But if I wanted to graph it, how would I go about doing it? Well, hopefully you remember the trick. We just have to complete the square in y, and that should do the job for us. I could do that by bringing all the y terms onto one side like this, and then asking myself, well, how could I wrap all that stuff up in one package so that y only appears in one place? This looks like the beginning of a squared binomial, so let me try writing one down and I'll balance it as needed. I could say, well, that kind of looks like y minus 1 squared. Not quite, because if I do y minus 1 squared, I would indeed get a y squared term, and I would get a minus 2y, but I'd also get a plus 1. So if I'm going to have that in there, I'm going to have to subtract 1 as well to balance the extra 1 that I pick up. Well, let me take that subtracted 1 and move it over to the other side of the equation. That would give me 1. And I'm done completing the square. And once I have my equation in this form, well, now it's easy to see what the graph looks like. That's a circle of radius 1 whose center is at 0, 1. So the graph would look like this. Okay, well, let's consider this problem. We want to find the polar equation of that circle. Unlike the last one, where the circle was centered at the origin and I could just look at it and say it's going to be r equals 1, this one will take a little bit of work, but not much thanks to our translation equations. To solve our problem, start with the circle's Cartesian equation and translate it over into polar coordinates, making substitutions from our translation equations. For example, x squared plus y squared. Well, that looks very familiar. That is r squared. As for 2y, well, this one tells me how I can rewrite y. Y is r sine theta. That means the right-hand side of my equation I could write as 2r sine theta. And now, in a sense, I'm already done, because all my x and y's have been translated over into r's and thetas. The one thing I can do to clean this up would be to cancel an r from both sides, giving me r equals 2 sine theta. Some of you might have balked at that operation and asked, wait a second, aren't you subtly assuming that r isn't 0? You have to assume r isn't 0 to divide both sides by it. That is true, but in this case it won't matter, because when r is 0 in the polar coordinate system, no matter what theta is, that corresponds to the origin. And the origin is already a point on this graph. Just let theta be 0, and we would have r equals 0, even after dividing that out. So we haven't lost anything by dividing by r. And that's good because this is such a simple equation for the circle. And there's a kind of a trade-off between this polar equation and this Cartesian equation. The nice thing about this is we've gotten rid of those squared terms and replaced them with nothing more complicated than the familiar sine function. On the other hand, you might say you like this one better because it doesn't have any trigonometry in it. As always, in different situations, one might be easier to work with than another, but at least now you know how to move back and forth between the two of them. And with that review out of the way, it's time to talk about doing a little calculus with polar coordinates. The idea is that if we're doing a double integral over certain kinds of regions, such as, for example, circles or sections of circles, it might be easier to describe the region of integration with polar coordinates. And in that case, we can translate everything over into polar coordinates and do our work in that system. For the most part, this is a straightforward process, but it all hinges on one observation. If we want to integrate over a certain region in the plane, and we're doing our work in Cartesian coordinates, then we imagine this region chopped up by a grid with lines parallel to the axes. So when we're talking about a little infinitesimal bit of this region, dA, we're thinking of it as being generated as follows. From any point, we get this little infinitesimal bit of area by increasing both coordinates by an infinitesimal amount. In other words, we increase the x-coordinate by an infinitesimal amount dx, and we increase the y-coordinate by an infinitesimal amount dy, which is why when we move from a double integral to an iterated integral, we always end up exchanging that dA for dx dy, or sometimes dy dx, depending on the order of integration. So far, so easy. But if we are not using the Cartesian coordinate system, but instead using polar coordinates, then my grid of infinitesimals that I'm breaking my region up into will have a different form. They won't quite be little boxes arrayed in nice horizontal vertical stacks. I'm still going to be generating my infinitesimal bits of area by starting at any point and letting both coordinates increase by an infinitesimal amount. But let's think about what it would look like in this case. My point is given by its two polar coordinates, r and theta. Now we want to imagine the little infinitesimal bit of area we will generate if we allow both r and theta to increase by an infinitesimal amount. We'll think about increasing r first. Well, that's easy. That just takes me an infinitesimal bit further away from the origin by an amount which we'll call dr. We have to be a little more careful about theta, because when we increase theta by an infinitesimal amount from the original position of the point, that's going to rotate it a tiny little bit counterclockwise by an infinitesimal angle, d theta. And these two forces together, the infinitesimal increase this way and the infinitesimal increase that way, will generate our new little infinitesimal bit of area, which might look something like that. Greatly exaggerated, of course. That infinitesimal bit of area will be our dA. But what will dA be in terms of dr and d theta, this little tiny infinitesimal increase in angle? dA is not going to be dr d theta. Think about this picture carefully. In fact, let me move the region out of the way so that it's not distracting. That's better. When I rotate this point through d theta, or through any angle for that matter, I'm moving it along a circle. So this edge of that infinitesimal box, this edge is on an infinitesimal bit of circle. Well, remember how we find the length of a bit of a circle. If we have a situation like this, a circle of radius L with a central angle alpha, then this arc length right here is going to be L alpha, provided that alpha is measured in radians. The simplicity of that formula is in fact one of the reasons why we like radians. And in case you have forgotten, this admits a very quick proof. The idea is that this arc length is a certain fraction, but what fraction we maybe don't know, of the full circumference, which is 2 pi times the radius L. What fraction of the full circumference is it? Well, it's the same fraction of the circumference that this angle is of the full 2 pi rotation. So that factor right there is just theta over 2 pi. It's theta 2 piths, so to speak, of the full circumference, which is 2 pi L. Well, the 2 pi's cancel, and we are left with L alpha, as promised. And note in passing the importance, once again, of measuring in radians here. If we were measuring in degrees, that would be 360, and this would not look nearly so pretty. I bring this up only because that is what will give us this length right here. This is a little circular wedge, like this one. It just happens to be on an infinitesimal angle. So that means that that edge of the little infinitesimal box is the product of that radius and that central angle. In other words, that edge must be RD theta. And now because this is infinitesimal, it is effectively rectangular. If it were finite and you made this angle and this length as small as possible, the smaller you made them, the more closely the little wedge shape would come to resemble a rectangle. Well, in the infinitesimal case, we can say it is a rectangle, which means that its area can be computed as the product of the two dimensions. So when I put those together, I find that dA is going to be r dr d theta. Pay close attention to that r. It is easy to forget, but very, very important. When we're working in polar coordinates, dA, the little bit of infinitesimal area, is not just dr d theta. It's r dr d theta. And this is a fact we will need every time we do a double integral in polar coordinates. So know it well. In fact, I will add it to our little box of formulas. Now let's put it to use. I want to give you an example of a double integral that looks very unpleasant in its native Cartesian form, but once we translate it into polar coordinates, turns out to be quite simple. Our problem is going to be to evaluate this double integral over the region R, where R is a circle, the circle of radius 3 centered at the origin, which I've drawn here. Now, before we actually solve this, let's try to identify the features of this problem that would make us think of polar coordinates in the first place. To begin with, we're integrating over this circular region, and circles, especially those centered at the origin, positively cry out for polar coordinates. Second, look at the integrand itself. It contains this expression x squared plus y squared, which we know from our translation equations is the same thing as r squared. And in fact, that will simplify further because the square root will remove the square and I'll just get an r there. That means this whole thing will become 3 minus r, and then I will pick up another r here because dA will be r dr d theta. So I'll be integrating 3 minus r times r, which is easy because that's just a polynomial. So before I've even started, I know this is going to be an easy problem to solve. In contrast, if I were to try this sticking with Cartesian coordinates, it looks like I would probably have a fairly long slog with trigonometric substitutions ahead of me. So let's take the easy way out and use polar coordinates. Here's my function restated. As always, I'm going to turn it into an iterated integral, but I'm going to do this in terms of polar coordinates. So the first thing I want to do is just write down the integrand in terms of polar coordinates. That will be 3 minus r, as we discussed a moment ago. Now we must remember, dA is going to be r dr d theta. And this is the stuff I will be adding up. I'm going to be integrating first with respect to r, and then with respect to theta. So let's do the integral with respect to r first, the inner integral. Well, I need to integrate as r runs from what to what? Well, think about what's happening over here in my region of integration. Take any old point in that region. Now, instead of the sort of thing we've been doing in the past, where we might have first integrated with respect to x and then swept this thing out through y, what we want to do is integrate first with respect to r and then sweep everything out through theta, as theta varies over a certain range. In other words, given some point like this, I want to just let r vary. I just get something like that. And once I've integrated along that radius, all values of r, running from 0 to 3 in this case, then I'm going to sweep that radius around and thereby pick up every point in the region. So first, integrate with respect to r. That means only letting r vary, keeping theta fixed. And we let r vary from this point, where r is 0, out to this point, where r is 3. So my boundaries of integration will be 0 to 3. And now I have to move on to my outer integral, where theta is varying. Now I just have to let theta vary from 0 to 2 pi. So the boundaries on my outer integral will be 0 and 2 pi. And now all the hard work is over. The rest is just a very easy double integral, because this is just a polynomial, and even my boundaries are just ordinary numbers. This will be easier to integrate if we multiply this out, like this. We'll bring down the outer integral, and I'll wait on the d theta to see how much room I need. And now we just need to evaluate this inner integral. Well, the antiderivative of that with respect to r is that, and we're evaluating, of course, at 0 and 3. There's the d theta. And when we evaluate this stuff, we get, let's see, that'll be 27 halves minus 9, which is 18 halves. So that gives us 9 halves. Meanwhile, when we pop 0 in there, of course, we get nothing. So I don't have to subtract anything off of that. And I'll just bring down the d theta. And now we're just integrating a constant. So that's going to be the constant function 9 halves times the length of this interval, 2 pi. So we will end up with 9 pi as the value of our integral. And that's that. Very easy. By the way, we could confirm this particular result using a different technique entirely. In fact, without using any calculus. Let's do that. What we need to do is to interpret this original double integral in terms of volume. This isn't something we can usually do, at least not in a way that would help us verify an integral without using calculus, but in this case it's very simple, and going through it should give us a little practice thinking about three-dimensional analytic geometry. So think about this function that we're integrating. Think about each term. Take the first term. If I were just considering the function z equals 3, well, that's pretty boring. That's just a plane in R3, namely the plane that is 3 units above the xy plane. This function that we're subtracting off it, though, if I thought of the function z equals x squared plus y squared under a radical, we've seen that one before. And if you don't remember it, you could recover it by going through the usual argument with cross-sections. If you set z equal to a constant, so you have that thing is equal to a constant, that would give you the equation of a circle. And the higher the constant, the larger the circle. And so you would end up with small circles down here and larger ones as we go up. And by playing with it a little bit, you could realize that it's not, say, a paraboloid. It actually represents a cone, which I've now drawn in. Now we're looking at the difference of these two functions. That would mean that for any particular point in the region of integration, which I've drawn in right here, for any particular spot in that region, say this one right here, we know how the double integral works. I take the area of a little infinitesimal neighborhood of that, my dA, and I weight that infinitesimal bit of area with the value of this function. But what's the value of that function? I can interpret that geometrically, because the 3 is the constant height from that point all the way up to the plane, z equals 3. But this second term that I'm subtracting off, that's the height from that spot straight up to the cone. So the difference of those two things, that's the big height up to the plane minus the little height up to the cone. Well, if I subtract those, I get something like that. So if I multiply that height by a little infinitesimal bit of area, I get the volume of this infinitesimally thin shaft through the cone. That's what this thing represents. If I add up the volumes of all of those little shafts that fill up the cone, well, of course, what I'm going to get is just the volume of that cone. What we've just concluded is that this double integral is equal to the volume of this cone. And the famous geometrical result, which you should all know, if you don't know it, just pretend you knew it all along, even if you're hearing it for the first time. This is a result that goes all the way back to Democritus. The volume of any cone is exactly 1/3 of the cylinder that the cone sits in. So I'll finish drawing in that cylinder. And I'll note up here that this volume is 1/3 the volume of that cylinder. As for the volume of a cylinder, well, of course you know that. That's just the area of its base times its height. Its base is a circle of radius 3, which therefore has an area of 9 pi, and its height is 3. So when you do the arithmetic, that comes out to be 9 pi, which is exactly what we got when we did our double integral with polar coordinates. Good, that means I did not make a mistake somewhere in my integration. All right, well, I promised you at the end of the last video that I would show you how to use double integrals in polar coordinates to come up with a very famous result. It concerns this function, which is a very important function. Its graph looks like this, and it lies at the heart of the so-called normal distribution from probability and statistics. So this function is everywhere where probability is. It's everywhere where chance is. Everywhere in any subject that involves random processes. It's a very important function. However, it happens to be a function that does not have an elementary antiderivative. That means if I asked you to integrate it, you wouldn't be able to do it. Now, it does have an antiderivative. Every continuous function has an antiderivative, but it does not have an elementary antiderivative. In other words, I can't write down an antiderivative for this function using the basic precalculus functions stitched together in the basic ways. I'd have to settle for something like that. It's a perfectly good antiderivative, but not elementary, since I have to use an integral just to write down the function in the first place. All right. What I mentioned in the last video was that even though this function has no elementary antiderivative, it is still possible to find the exact numerical value of the integral of this thing when we integrate it over the entire real line. That would correspond, of course, to the area under this curve. And if you've had some probability and statistics, you might be thinking, oh, it must be 1. It isn't 1. This isn't quite the function that gives us the normal distribution. It just lies at the heart of it. We have to change it a little bit to make it what's known as the density function of the normal distribution. But the question remains, how do I actually come up with this thing without having an elementary antiderivative for that function? What you've been doing as long as you've been studying integrals is to evaluate any definite integral, you use the fundamental theorem of calculus. You get an elementary antiderivative for that thing, and then you evaluate at the endpoints and subtract. Well, forget it. There isn't an elementary antiderivative. We have two mysteries. How can I evaluate that thing exactly? And what will the exact value actually be? And the third mystery would be, what does any of this have to do with double integrals in polar coordinates? Well, I'll show you. I think you'll like this. It's a very clever argument. First thing I'm going to do is, I don't know what the value of this integral is, but let me just give it a name so I don't have to keep writing this symbol down over and over. Let's let I be the value of this integral, and our job will be to figure out the numerical value of I. Well, to get started, I want to remind you something about definite integrals in general. The variable that appears in them is a so-called dummy variable. These three integrals, for example, all represent the same thing. In each one, we're taking a particular function, the squaring function, and integrating it from 0 to 1. X is just a placeholder. Same story if you did it there. The fact that I called this t instead of x doesn't change the integral. Same story here. Even this represents the exact same thing, but is too silly, so please don't put anything like that on an exam. That means that the x here and here really don't mean anything. If I replace them both by y's, I would still have the same integral. If I replace them both by q's, I would still have the same integral. Just a dummy variable. I mention this because the trick we will be using to crack this integral depends on that innocuous sounding principle. What I'm going to do is work with I squared instead of I. That's going to be two copies of this integral multiplied together. But I'm going to write the two copies in slightly different ways. The first factor will just be exactly what I have written above. But for the second factor, I've swapped the dummy variable. I've used y instead of x. This might look like a peculiar thing to do, but it's going to be very useful to us. It may be strange, but there's nothing wrong with it. I'm just representing the same sum two different ways, as if I were describing the integral once in English and once in Japanese. It's still the same underlying thing. Now let's just concentrate on the first factor right here. We don't know much about it. In fact, that's the whole point of this problem, is to figure out its value. But it has some value. It is some number, we just don't know what it is. And we know that constants can be pushed inside or dragged out of integrals. If this were just the number 5, well, I could push it inside that integral and have a 5 right there. If this were the number 17, I could push that inside and have 17 times that stuff. I don't know what its value is, but it's a constant. So I'm just going to push that whole thing inside that other integral and write it like this. This whole thing is just some constant multiple of my function of y that I'm integrating with respect to y. And now that I've stitched these two integrals together, I can make another interesting move. This e to the minus y squared. Well, as far as this integral is concerned, since this is an integral with respect to x, as far as that integral is concerned, this is a constant. It's no different than if it were 42. Accordingly, I can take this factor and move it in and out of this integral, since it's a constant as far as that integral is concerned. Now, I can't move it out of this integral, because of course it is not a constant when we're integrating with respect to y. That's the whole point. But let me go ahead and push it inside of that integral. And now I'm going to go ahead and get rid of those parentheses, as we generally do in these cases. Okay, how is this going to help us? Well, take these two factors. Let's combine them like this, just using properties of exponential functions. And now you're getting your first hint of why polar coordinates might help us, this x squared plus y squared, which of course makes us think of this fundamental relationship that r squared is x squared plus y squared. Well, I already have an iterated integral in terms of x and y. If I wanted to possibly turn this into a polar integral, the first thing I'm going to have to do is turn this thing into a double integral, and then from there, turn the result back into an iterated integral done in polar coordinates. So let's see. I need some more room. If I want to write this thing as a double integral, so just having dA there, I need to think about what the appropriate region of integration should be. Well, I'm staring at it right here. If x and y are both running from minus infinity to infinity, then I am integrating over the entire plane. So my region of integration for my double integral would be all of R2. Good. This sets me up to translate over into polar coordinates very easily, because my integrand will be e to the minus r squared, which isn't a surprising thing to see given the function that we are actually starting with. But the wonderful thing here is what happens to dA. As always, dA, when we turn it into polar coordinates, becomes r dr d theta. I say this is wonderful because even though I can't integrate that thing with respect to r, I can definitely integrate that thing with respect to r. We'll carry out the details in a moment. But first we need to get our iterated integrals up there. What will our boundaries of integration be? Well, the inner integral is integration with respect to r. So as we did before, think of a particular spot in the region of integration. I have to cover the whole plane. Well, I can do that by first just integrating with respect to r, which will give me this whole ray emanating from the origin out to infinity. And then I want to take that ray and start when its angle theta is 0 and sweep it out through the entire plane. And when I do that, I get every point in the plane. I cover the entire thing. So my boundaries of integration, r is going to run from 0 to infinity, and theta is going to run from 0 to 2 pi. Well, this, as we've said, is an easy integral. You could do it very formally by substitution, by letting this thing be u, and that means du would be 2r dr, which would be something like that. But I don't want to write down the little dictionary between r and u. And by this point in your career, you can probably just play the game of guessing a likely antiderivative and making little adjustments as need be. So let's try it out in this case. We want an antiderivative for this. Well, it should look something like e to the minus r squared, based on what we just said a moment ago. So let me start by just writing down e to the minus r squared. Will that do the job? Well, not quite, because if I took the derivative of this, I would get this function back, but then I would also get a minus 2r when I carried out the chain rule. Well, I like that r that appears because I want that up there, but I don't want that minus 2 in there. So I'm going to need to balance it by a negative 1/2. So I'll put that in right here. So that thing is an antiderivative of our function. That means I just need to evaluate it when r is 0 and infinity, and bring down the d theta, of course. Well, this is easy to evaluate because when we pop infinity in for r, we get e to the minus infinity, which of course is 0. So this whole thing becomes 0. So I would get a 0 there. and then I subtract off the result of popping in 0 for r. When I put 0 in for r, this whole thing becomes 1, so I get minus a half. So I have 0 minus a half d theta. Or in other words, the integral of 1/2 as theta runs from 0 to 2 pi, which is of course half of 2 pi, which is pi. But what is this thing we just computed? You may have gotten lost somewhere along the line. This is equal to this, equal. It's I squared. So since I squared is pi, it follows that I is the square root of pi. And I, of course, was our crazy integral we started with in the first place. So we now know that this integral is the square root of pi. Well, this is remarkable. We've taken this function that has no elementary antiderivative, yet found its definite integral over the entire real line, and the result turns out to be the square root of pi. Very interesting connection between these two fundamental constants, e and pi, and it's mediated by infinity. Well, it's hard to come up with a better way to end a lecture than with a result as nice as that. So until next time, sayonara.